much. First of all, can you hear me? My voice is kind of gone. First of all, I'd like to thank my mentor, Professor Lakshmi. I am one of his early students. And actually, it was a great honor and pleasure to be here and talk about something totally different. I'm going to talk about something that you may have not even heard, or even maybe you have heard a little bit, because the Titan submersible that got crashed, reported a couple of years ago. So I'm hoping at least today, at least few of you will get excited about what we do. This is all about underwater robotics, and I'm going to talk about how you use underwater robots around the world to deal with scientific challenges, underwater challenges. So I put together a small roadmap. So first we learn about some basics of underwater robots and its own challenges in making those robots. Then we are going to explore underwater challenges and other challenges using underwater robots. And some fun stuff if I have time. So I want to stop by around 3:45. So let me finish my talk before I take questions. That way I can show everything what I have to show you. And if you don't have time to answer, just Google, you will get all about it. You can learn all about it, all what you need the interest. So even though we say underwater robots, actually the official name is ROVs, remotely operated vehicles. That means that this one is an unmanned, very sophisticated instrument that can be driven inside water and doing all kinds of stuff. Those can be big and small. So this one is about, the weight of this one is about 5 tons. Weight of that one is about 50 pounds, and that's what we made. So I'm going to talk about those. So this one you just throw it away. This one you need a big ship and a crane to take it to water and put it into water. And then I want to show you some parts inside the ROV. So I'm going to call it ROV now. So here's a chassis, like a frame, like your car, where everything gets attached to. And these are called thrusters. That's kind of the engine of this thing that makes it move. So this particular one is called Defender. That one has 7 thrusters, 4 to go X and Y axis, and 3 to go Z axis, go up and down. And you can control that each thruster individually. That means you can do whatever you want, like this, go back and forth, all motions. And then it has camera to see. So this is connected. How do you operate? This one is operated through another controller, which is not in water. It's somewhere else, connected through a wire. That wire is called tether. So there's a camera to see what's out there, and then some couple of other important modules. This is called a power module. That is the module that takes power from the top of the controller and convert that into lower voltages to work used for all the other modules. And there's another piece called communication modules here. That handles all these complicated communications, the videos and all the other stuff. There's so much stuff going on in this thing. And this is called AHARS. I'm going to show you all this stuff in my next slides. It's a very fancy compass. It knows exactly where you are. And there's another one I want to talk about, is a sonar module. That is when there's no light, there's no camera, right? You can't see anything, all dark. But instead, like dolphins, it uses sound waves. And you send out sound waves, and if I send sound waves, there's echo coming from each of you, then I figure out, okay, there's someone here. It's like that. So most of the time, you are driving this with the sonar. And a couple of other modules, there's I want to show you. There's another one called Doppler velocity logger. I'll talk about that later. That one helps you to keep this vehicle very steady in water. and a couple of other stuff that I can talk about a little later. And the whole system is that ROV, and the controller which sits somewhere else connected to this wire is called tether. And it's all, you operate the ROV with this joystick. I don't know if any of you have done any video gaming in the US. All the adults and young kids, everyone has done video games. I haven't, because I didn't grow up in the US. But in the US is like that. And this is how it works. You take the whole thing and then throw the thing in the water, and you operate it from here by watching the screen. Screen shows the picture of the live stream from the video and also the sonar, and also shows you all the statistics, all the status of all the modules that it was in the, I showed you earlier, all the time. So the main challenges of designing a ROV is, the first one is the water pressure. So when you go in water, there's a water above you. That puts you on huge pressure because the water is very heavy, right? So how it works, right now it's like approximately 1 atmosphere here, but if you go down 33 feet, it adds another atmosphere, 1 atmosphere, so that means 2 atmospheres. So if you go to 100 feet, I think it's about 4, so that means every 10 meters, 1 atmosphere. If you go to 40 meters, 5 atmospheres. So divers can go only up to about 5 atmospheres, because after that you need to have very special gear to wear, and even then you can go another 2 more atmospheres. So that's one of the problems, huge challenges. When you design something go underwater, it has to withstand all that pressure. So that, you hear about the Titan? Okay, so that's happened. They couldn't figure out they didn't design it correctly. And the next one is water tightness. It has to be 100% waterproof. So Titan, they figured the waterproofness part, but not the weight of the water. And often in the oceans, it's all corrosive environment, so you've got to worry about that one. And also, unpredictable water currents. And then the recovery. So because this has a wire, you can recover, right? It gets stuck somewhere, but it depends how you went there. If you've gone through some obstacles, then pulling it back could be very, very difficult. And you really want to recover, because the price of this thing is about $250,000. Okay, I'm going to skip that. So the technical difficulties of designing the ROVs is power delivery, the communications, and stability and harsh environments. I'm going to talk a little bit about these three. So power delivery. So from the top, I have this controller, then ROV is in the water. I need to send power to that, so that needs some power, right? But it's not from here to here, it's from here to 3,000 feet down. That's almost more than half a mile. So we have designed this to go to 3,000 feet, but we have rated that for 6,000 feet. So sending power through 3,000 feet away is a big challenge. I don't know whether you have done how much you have exposed to all the electronics and power and stuff. So when you send some power, meaning some voltage, and send some current, when the voltage is higher, you send smaller current. That's the way you need to do that, because when the power goes through this wire, the current goes through this wire, get wasted as a heat. So higher the current, higher the wastage. So what we do is we want to send smaller current, meaning we need to increase the voltage. So in this case, we use 400 volts. So 400 volts, in that thing, when you hold something 400 volts, we got to make sure it's not leaking. Just simply you want to shock, right? It will be dead. So we go extra 200 miles to make sure that if there's any leakage, it gets stopped. So we figured out some numbers. At 400 volts, if you are exposed to 50 microseconds or longer, your heart will stop. So we have to detect any leak within 1 second, 1 microsecond, which we did. So our system, it detects any leak, whether there's a leak, all the time. It's like 100 million times a second. And if there's any leak, it stops. And that's how we protect it. So this I'm showing you that it's pretty dangerous stuff. And so I had to design a 400 volt converting from 400 to 48 volts, because the 400 is here, 48 is inside the thing. So we have to convert that 400 to 48. Are we okay so far? Okay. And so I did the research. I'm just taking one example because you guys are doing research. You know how you get frustrated. You know, I've been doing that like that some time ago, long time ago with my professor. And you are talking about molecules and atoms and stuff, right? But I'm talking about all the electronics, the wires and all this stuff. That's why I'm showing you this kind of thing. Otherwise, we'll be looking at some UV spectrometer or something like that. So I did the design, and then so we are converting 400 volts to 48 volts at 1500 watts. That means you're losing some heat. That means all electronics, that's the converter that I designed. It gets hot. So what it gets hot, but the thing is that as long as you transfer that heat to its housing or whatever it's holding up, that thing is in water. So no problem, you can convert with the heat. So the R&D part, I did my research, everything worked, and then do my testing. And then this is the housing that I showed you a module, that's a module. So we put that thing in there, then you have to make it, this is how it looks like. So this is the tether wire, it comes through here, it gets converted and feed into other ports. So now we have to make this watertight. How do we make it watertight? Are you familiar with potting? So this is the resin. So you take a couple of chemicals, mix together, become a liquid, and then you pour that into that thing and cover it. After about 2 days, it's all like a really solid, completely like a solid waterproof device or the box. So it all worked fine for 3 days. After that, it started failing. Then I had to figure out what's going on, and I can't do anything because it's all sealed. So then, when we designed this, it's all modeled, precisely modeled. So then, using the model, I figured out, how do you find out what's wrong? You have to probe into all these electronic, the little chips. But I don't have access because it's all sealed. But I use the computer model to figure out X and Y, Z coordinates, and to pinpoint a particular chip. So now I drill all these holes. So that way I figured out what's wrong. What's wrong is when the epoxy gets cured, meaning when it dries up, sometimes it pulls up all the chips. And it's very random. It's something here, something here. So it takes about 3-4 days. That's why it fails. Then we changed the potting material. So this potting material that we changed, they call it re-entrable, meaning it gets solidified but not 100%. It solidifies about 80%. It's like a very, very hard marshmallow. So it's this little bit softness. And if I really want to open up, I can dig in and open up. So now, then I was very curious and look at the chemistry. What's the chemistry behind it? You probably understand this way better than me. So this is 1,3-butadiene and go through polymerization and then makes this. This is the final re-entrable material. And it says that here, cis bond makes bending chain, meaning it's soft. I don't know, maybe Lalit can tell me what that is. So the next challenge is the communication. There's a lot of information and that ROV, you have to bring it up here. And 3,000 feet is long ways. So, and whatever happens there, when it comes here, there's a delay. So if you're looking at the camera and drive this, what you're using is like a 2 seconds delay. So that's not very accurate. So we had to go through, change it to fiber optics. We have heard about fiber optics, right? So it's another headache, how you deal with all that stuff. But anyway, so we figured all that. Then we had to worry about the stability. So when you drive the car on the road doesn't move. Your car moves, right? So no problem. But this one, no. Road is also moving. The whole thing is moving independently. So the navigation stability is a crazy thing. And so there are some technology there. So one is called DVL, Doppler Velocity Logger. Have you heard about Doppler velocity, Doppler effect? This is the Doppler effect. And using that, you can always measure the speeds in all three axes, this way or that way. And then the direction we are going, southwest, the direction, we need the speeds and also direction. So for that, there's something called AHAS, I'm going to show you pretty soon. And the third one is GPS that I use in your cars. And how the Doppler velocity logger works, this one, that one sits under that ROV, pointing that way. There are 4 sonar beams, meaning sound, that emit sound beams, and 4 different angles, and figure out the frequency change. So by monitoring all that, by looking at the shift of frequency, you can tell whether they are moving away or closer. So by looking all that and analyzing all that, this device can tell the ROV whether it's moving that way at what speed or this way at what speed. So when you know that information, you feed all that to thrusters which make it moving, right? So if it moves that way, the thruster which is going to pull that way, so it comes back here. This is what I'm saying. So by feedback mechanism, you can make it steady, very steady. And so AHAS is something called attitude and heading reference system. These are all electronics. And so in that particular sensor, there are some little device, it can detect the acceleration, like your car, on all three axes, and also the angular acceleration, whether it turns this way, how fast it does. So what's acceleration this way or what's acceleration this angle. And also the Earth's magnetic field. With Earth's magnetic field, you can figure out whether you're going east, west, northeast. With all that information, you can get accurate information about this vehicle all the time. So that helps you make the ROV stable. So this one shows you the picture. This is a plane, lying in water in this ocean, and so this is how a sonar, the sound waves. This picture was generated with sound waves. This is how the dolphin sees these things. So when there's no light, the sonar helps the pilot to drive the vehicle. Then I want to talk about scientific challenges. Have you heard about nuclear power generation? So what they do in nuclear power generation is they use nuclear power to boil water. Then you make steam, and the pressurized steam, then use that steam to generate run the generator, creating power. But then they use something called nuclear rods, and the nuclear rods, they sit in water, and people cannot touch it because they are radioactive. Right? So they use ROVs to handle all those nuclear rods. They move around. They have to, every year you have to change nuclear rods. So you move somewhere else. So humans cannot do that. Only the robots can do that. So this is one of the robots that they use to do that. This is one of the nuclear power generator near my office. I just took a picture to show you that. This is something called aquaculture. Aquaculture means the things you do with water, so fishing, and I'm going to show you what they do in fishing. So in fishing, large-scale fishing, I don't know that you have heard these things. So this is a huge net. Underneath, inside the water, there's a big net. The harvest of this net is about 5 tons fish, that many fish. So when they harvest, that's such a big catch. You want to make sure that there are laws too, regulations that you don't want to catch young fish. You want mature fish. One thing is if you catch all the young fish, they won't sustain, right? The other thing is the profit. If you catch young fish, you can't make that much money. In the past, what they do is these nets, they size the hole of the net so that when they lift it up, the small fish can escape. But that's not really efficient. So what now they do is, have you seen ultrasound pictures of babies in their mothers? They use those ultrasound cameras, use ROV and go inside and take pictures at various points. There's a way to do that. But randomly they take some about 100 pictures of fish. They can see the bone structure of the fish. So from the bone structure, you can figure out the age of the fish. So they have some statistical this methodology that they do this and figure out, okay, the 80% of the catch here is natural fish. If that's the case, then they harvest it. So they use this our underwater robots to do all that stuff. Have you heard of these things? Yeah, me too. But now doing all this stuff, now I know. We don't do all this stuff. So some companies, they buy our instrument. That's what they do. Then they tell us what they do. The other one is something called ultrasonic depth sensing. This is very important in ship industry. Ships, like your car, every year you have to do the inspection. Meaning they have to check the hull. Hull is the bottom part of the ship. The thickness of that metal has to have some specific thickness. So using ultrasound technology, you can detect the thickness of the metal. So what they do is, if this is the metal, you put the sensor here and send some sound waves. So sound waves goes through here and comes to this end and comes back. So by calculating the time which to go and come back and knowing the speed of sound of this material, you can calculate the thickness. So that's what they do. So our ROVs can do that. See, there's a sensor there. So they use our machines to completely scan the hull of the ship and then certify whether this meets all the specifications. Next one I want to talk to you about is something called cathodic protection. And remember, you look at the periodic table long time ago, your chemistry, right? So periodic table, I remember that there were some metals order what is more active versus others. So in real world, there are a lot of structures inside water, from pipelines or bridges, but they go through corrosion. To prevent corrosion, what they do is they put a more active material, like in this case, this is more like steel, this is either magnesium or zinc, and they make like a battery and make this side as an anode, this is the cathode, and only the anode gets wasted. So you can protect the pipeline that you want to protect. But sometimes the circuit is not working properly, so corrosion starts here. So what we can do is, in our system, our unit can go and look at the current and figure out what's wrong with the circuit. So it's called cathodic protection. So these are all underwater challenges, very difficult to do otherwise. So some other applications that I want to talk about is, we call it first responders. That is when people drown in chill, very, very cold water in the US and Europe. Divers can go find the bodies. Instead, they send these ones. And so because they have these units, we have sonar systems, we can detect the bodies very quickly and then retrieve it. see your case I want to show you about. And hydroelectric dams. We have hydroelectric dams here, and those hydroelectric dams, there are a lot of many underwater structures that we got to go inspect time to time. And some years ago, our sales team told me that they got a call from Sri Lanka. They want to know whether they can, use our ROV, because one of these dams here, maybe I don't know, maybe Victoria, that they have a crocodile infestation. So they need to go and see what's going on with the crocodiles and what's happening. And I don't know what happened, but then I want to show you something else. This is about defense. So US Navy uses our systems to detect underwater sea mines, land mines. So these are sea mines. They are not there yet, but they are getting ready for it. When that thing happens, they can detect it. So our robots can go find sea mines and then destroy it or neutralize it. And that's a very big thing in the US Navy right now. So they just ordered 400 of our units to build a platoon. So they go underwater and detect. And also another program what they have is, they have 100 dolphins. We don't hear all this stuff. They have 100 dolphins and 100 sea lions. They have trained, the dolphins and sea lions are very smart. They can be trained very easily. So what they do right now, they're training. They use our robots. Our robots can detect landmines very quickly, big area, and they want to teach dolphins to how to map these landmines. Like there's one here, there's one here, there's one here. Like the landmine, you map landmines like sea mines. You could map it. So what they do is they send our ROV and then ask the dolphin to follow that. And dolphins carry a little number tag, and they attach that number tag to each sea mine. So they are all practicing. There's nothing there yet, but they're practicing. Then I want to talk to you a little bit about the future of these underwater robots. So right now we are thinking of making flyouts, meaning our ROVs stay inside water permanently, and then time go, whenever it gets a command, it goes out by itself and do some tasks and comes back and report it to the top. So that's our latest product that I'm supposed to work on when I go back. And the other thing that we are thinking is, it's called unmanned service vehicle. So this is a boat. It's all AI-driven boat. Sits around the world, many places, strategic places, with a ROV on board. And so whenever it gets command, this boat goes to a certain place and then gets deployed. This one automatically and do whatever is necessary. I don't know what they want to do, but we are ready. We are getting ready for it. Then I want to talk a couple of fun stuff that I did. So a few years ago, the Indian Navy bought 7 of our systems. Each system is $250,000. So I felt India is up to something to spend that much money. But anyway, the deal was that when they delivered that, when they received those 7 units, 2 people from our company has to go there for them to test with them. And I was one of the scientists went with them. So my friend and my company friend and we went to Indian Navy, spent 2 weeks in India with the Indian Navy. And so they want to test these units at 1,000 feet. And so we were in Mumbai. It's called Bombay, right? It's called Bombay. So you have to sail about 9 hours to this spot to get this 100,000 feet depth on the ocean. So we spent 9 hours on this ship. This is a missile launching, US Indian Navy ship. I was on that for 9 hours going that way and that way. And so the captain of this ship, because before I came to this ship, they had all our records. I had to tell where I was born, and he knew that I was from Sri Lanka. He ordered Sri Lankan food for the whole ship all the time. I didn't know that, and I was very touched, what he did. Uh, do you remember this? Costa Concordia wreck. That happened about 10 years ago. I don't know that you remember that in near Italy. The ship went back just like that. You probably not paying attention, but I'm sure hereafter you might pay attention now that you have heard all these things. So this happened about 10 years ago near Italy. And so they use lots of underwater robots to monitor inside. And one report it said that, like in Sri Lanka, some divers went underneath and started stealing money from the slot machine, ATM machines that they had on this cruise ship. Now I want to show my last video. This shows you how our system goes and finds a landmine, a sea mine, and destroy it. That's the name of my company.